This is the effect of X on the iodine partition coefficients. It is the first in a series of videos I'll be doing on ideas to support, catalyze a fantastic internal assessment from you, the students. Mr. M for Chem, comment, like, subscribe in the normal manner. Thank you. Okay, here's the chemistry. We've got iodine in an aqueous layer, solubilized in potassium iodide. We'll come to that very shortly. And that's in equilibrium with iodine in cyclohexane, C6H12. As chemists, you will know that cyclohexane is a non-polar solvent, and the aqueous system is a polar solvent. So you would expect some different interactions between the solute and the solvent in both of those systems. And that's indeed what we are studying. We also can write a solubility expression, or just a Kc or a Ka or a Kb or a Kw, products over reactants. You know this, you get the idea. It's the same thing. So the partition coefficient is just the equilibrium expression, the same as what you've done in class. So here we've got products. It is our iodine in cyclohexane divided by our iodine in the aqueous layer. Now iodine I2 is a simple molecule, and you would know that does not dissolve readily in water because like dissolves like. And I2 is non-polar, and water, as you know, is a V-shaped molecule and is a highly polarizing molecule, polarized itself. So we react the I2 with I- to make the I3- ion. That makes the I3- ion stable in the polar solvent, which is water. Let's have a look. What could X be? Because I'm talking about the effect of X on the iodine partition coefficient. The classic one to do will be temperature. Obviously, at higher temperature, you'd expect more to go in. You might be wrong. Maybe get more to go in. And at lower temperature, less will go into solution. You can look at change temperature, 5 different temperature ranges, temperature values. Do it in triplicate. You're on the way to a fantastic IA. If you are very well stocked and you have an excellent solvent cupboard, you can look at the solvent polarity, maybe even dielectric constants. There's an idea. Or look at the pH of either of the solutions and changing the pH. Easiest to do for the aqueous system, of course, because many of the solutes, their ionization is pH dependent. So there's a few ideas of how you could approach an IA using this system. How do you do it? Well, here are the details. In these videos, I will show you the details and give you the fine print on how to actually make it happen. Take 50 cm cubed of 0.05 mole per decimeter cubed iodine solution dissolved in Ki. What does that mean? Well, you need to get 0.05 moles of iodine, but that's going to be in 50 cm cubed. Notice how I have done the uncertainty. It's the same number of decimal places in the uncertainty as in the value. If you don't do that, you are at risk of being marked down by your moderator. We've got 0.05 mole per decimeter cubed in 0.05 decimeters cubed. Don't forget to keep your units consistent. It gives me 0025 moles of iodine. The atomic mass, or molecular mass in this case, of iodine is 253.8. Multiply those together to give me the answer of 0.6345 grams of iodine crystal to dissolve in my potassium iodide. How much? We'll do that next. To make a 0.05 mole per decimeter cube solution of iodine. The potassium iodide just need between 2 and 3 grams. Okay, we don't need to know that accurately. We don't need a specific number. Just somewhere between 2 and 3 grams, a few spatulas worth, and it will help to dissolve the iodine completely. It takes a while to get it into solution, but I know that you are tenacious and resilient, right? So dissolve the 0.6345 grams in the Ki solution. You'll form your I3-. Pop it into a 50 cm cubed volumetric and make it up to the mark. Next, you're going to get your cyclohexane. Cyclohexane, you're going to pipette onto the top of the iodine. You can see on the picture on the screen, the opacity has been reduced, but we have the pink layer at the top. That's going to be the cyclohexane, and kind of a golden brown color at the bottom. That's going to be the aqueous layer. You need to shake it really vigorously for 2 minutes. Make sure you control that variable for 2 minutes. Let it stand, let it sit. The layers will separate out, and you will hopefully see a very clear line between the two phases. Okay, take 10 cm cubed of the aqueous layer and then titrate that against 0.05 mole per decimeter cubed sodium thiosulfate. Of course, in your IA, you will standardize that thiosulfate to validate, to prove that it is actually 0.05 moles per decimeter cubed. We're going to add starch solution, and the endpoint is colorless. So as you're running in the sodium thiosulfate into the aqueous layer, it will turn a slight shade of brown. That's the iodine being precipitated. Put your starch in then. It will dissolve beautifully, unlike the other one. We'll come to that in a second. And then when it decolorizes, that is the end point. Okay. Now, for the cyclohexane layer, it's more difficult because the cyclohexane, as we said, is non-polar. Starch does not want to dissolve in cyclohexane. Neither does the sodium thiosulfate. So when doing the cyclohexane layer, and this is an error you can talk about in your evaluation, you need to shake it vigorously again and really get some elbow grease into there to get that system moving to allow the starch and the thiosulfate to surround the iodine in the cyclohexane. So constant swelling is critical here. The endpoint is the same. It will be colorless or decolorized from blue, black. Here's an exemplar results table. Hopefully this is enough to get top marks. I've been looking at the criteria. I have my decimal places consistent. There are 2 decimal places throughout. My uncertainty is of the burette, 0.05 cm cubed. Maybe you can see I've made an error. I did this on purpose. The error is that there are only 2 repeats. Okay, there's the rough titer. There should be 3 repeats, but you get the idea here of what we're going towards, and I'll give you an idea of the calculations you need to do in just one moment. So it starts with 13.1, 12.8, 12.9. The mean of those two is 12.85. 12.85 plus or minus 0.05 centimeters cubed. So moles of thiosulfate, NaC times V, concentration was 0.05, and my titer volume was the mean, which was 0.01285. We can see the answer is 6.435 by 10 to the minus 4, and that's moles of thiosulfate. But what's the ratio of thiosulfate to iodine? Well, here's the chemistry again. We've got 2 to 1, haven't we? 2 moles of thiosulfate with 1 mole of iodine, because the 2 electrons given off by the thiosulfate are taken in by the iodine. So we balance the electrons, and it's 2 to 1 reacting ratio. So from the thiosulfate to iodine, we need to half it. It's also, many people miss this trick, it's in 10 cm cubed. So it's 3.22 by 10 to the minus 4 moles in 10 cm cubed. But in a litre, it's 3.22 by 10 to the minus 2. Yes. Okay. So, I think that was a mistake there, wasn't it? I didn't put the 2 there, I put the 4 there. It should be 10 to the minus 2. That's what threw me. So it's 3.22 by 10 to the minus 4 in 10 cm cubed, correct. But there's an error there. It should be 3.22 by 10 to the minus 2 in moles per decimeter cubed. The cyclohexane layer, the table looks the same. Remember, the concentration was different for the cyclohexane. We have C times V, concentration 0.025, not 0.05 now, and it's 0.1120 with the mean of my 2 concordant results. Again, that's in 10 cm cubed, so we half it, and we go from 10 to the minus 4 to 10 to the minus 2. We then just do products over reactant. So we've got our 1.4 by 10 to the minus 2 for the cyclohexane layer. Divide it by the 3.22 by 10 to the minus 2 for the aqueous layer. I get an answer of K being 0.43. So that's exactly how you do it. You just have to change the temperature, change the nature of the solvent, change the pH, and you're on the way to a fantastic high-scoring internal assessment. Of course, half the marks now are conclusion and evaluation. So what are the pitfalls? What are the things you could be talking about? The things you need to be aware of was we shook the funnel for 2 minutes. Was that enough? Did you do a trial for 1 minute, 2 minute, 3 minute, 5 minute, and see if there was more or less iodine dispersed, dissolved, solubilized within each of those systems? That would be a great thing to do, just to show that you control the variables. The thiosulfate, any solutions that you use, you should standardize and verify, validate that the concentration is what the concentration you are using within your calculations. The cyclohexane thing, a problem is just an opportunity, right? Because that gives you fantastic stuff to think about and to speak about in that all-crucial evaluation, which is 1/4 of the marks. And don't forget, I only did 2 repeats. Okay, hope you found this useful. I will do some more on accessible experiments which are appropriate for high scores on chemistry internal assessment on the IB diploma. Thanks very much for watching. Have a great day. Bye-bye.